Taylor and McLaurin series. So we're going to finally figure out how old is this amazing series we found and created. We're going to teach you how to create others. Let me start with saying that if we represent f of x as a power series, we're going to do it like so. F of x equals, and we already know what it means to be a power series. The first term, the first coefficient, let's call it c sub 0, plus c sub 1, x minus a to the 1. That's the formula with the shift. I gave it to you. Power series with the shift. Plus c sub 2, x minus a to the 2 squared, plus c sub 3, x minus a cubed, plus, and keep going. Then, check it out what we're going to do. Very interesting idea. This material is taught exactly in this way. Maybe sometimes they call CAs or anything else. The same way. Whatever I'm telling you right now is taught in Japan, Ukraine, France, and my favorite one, even in Canada. So, this is pretty cool. I remember this, how I was a student, and watching this, none of it made sense. But then it did. And when it did, it clicked how amazing it is. Let's find the first derivative. F prime. C sub 0 gives you 0, so I'm skipping it. C sub 1 is now multiplied by 1. Because x minus a, x prime gives you 1, a prime gives you 0. Plus, this 2 goes down, decreased by 1. So it's going to be 2 c sub 2, x minus a to the 1. Plus, the 3 goes down, it decreases the power. 3 c sub 3, x minus a squared, plus, and keep going. Very interesting. So we're going to do more, but I just wanted to point out that powers are all increasing correspondingly. And then the number in front is 1 unit higher. Let's find the second derivative. The second derivative is c sub 1 goes away. Derivative of c sub 1 is 0. So now we will have 2 c sub 2 standing by itself, right? Because x minus a prime is 1. Plus 3 times 2. Because this 2 now also goes down, but multiplies by 3. Maybe let's color code it, 2. C sub 3, x minus a. And now it's raised to the 1. Can you tell me the next one without seeing it from f prime? Do you know what the next one will look like? Can you guess? So it's going to be 2, yes? Times what? You already told me c. I definitely know it's c sub 2, c sub 3, c sub 4. Now you told me 2 or 4. Which one? Are we going down or up? Up. So 1 up, exactly. Because this original one was 3. Now it will be 4. 4 times what? Times 3. Amazing. Because 3 will go down. C sub 4, x minus a to third. Yes or no? Squared. Good job. Let me check. Showing you this. Let me change the color. So 1 is now attached to c sub 3. 2 is now attached to c sub 4. 3 will be attached to c sub 5, and so on. While before it was 1 was attached to c sub 2, 2 was attached to c sub 3, and so on. So derivative keep changing the counting. That's the second derivative. Let's find third derivative and make a conclusion. There is definitely some kind of pattern. We're trying to find a pattern not just in each power series, but pattern between derivatives. That is a pretty cool idea. Because derivatives are also creating a sequence. F1, F prime, F prime prime, F prime prime prime, creating a sequence. So they also have their own pattern. 2c sub 2 goes away. So I'll write down 3 times 2 c sub 3. That's my new isolated standing coefficient. Plus 4 times 3 times times c sub 4 to the more. 2 goes down. So it's going to be times 2 c sub 4x minus a to the 1. Keep going. So as you can see, we keep moving to the right with the isolated coefficient, and we have a pattern. We do have a pattern here. 4, 3, 2, 1, 3, 2, 1, 2, 1, 1. So we can see some kind of counting pattern because of the power rule. Now, we're going to remember this. This is important. And we're going to plug x equals a. X equals a. The smallest convergence set. That is also the smallest convergence set. Convergence set. This is something you might not remember, but I mentioned to you before that all power series converge to the center. So even in your homework you had series that diverge everywhere and the radius of convergence was 0, it still converges at A. So it's the smallest convergence set. Like at least it converges there. So let's plug A everywhere. Then let's figure out what's the f of A will look like. F prime of A. Why my f is so ugly today? F. What is f prime prime at A? No, it's the third one. F prime 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 at A. Like so. We're gonna plug A everywhere. Let's do it right away. Check it out. If I plug A into f of x, what do you think will stay? Just c sub 0. If you plug A, this is 0, this is 0, this is 0. Everything is 0 except c sub 0. So basically the isolated coefficient stays. That's why power series converges to the center. If you plug the center, at least the coefficient stays. So that means it converges to that coefficient. How about f prime of A? C sub 1, right? 0, 0, 0. C sub 1. How about f prime prime at A? 2, C sub 2. How about f prime 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 at A? 6C3. Let's keep it as 3 times 2 because it looks like a nice pattern. 3 times 2, C sub 3. Now, do you know, by the way, how to write down f, the fourth derivative? It's not 1, 2, 1, 2. Nobody does that, actually. People start putting numbers in parentheses. That is a reserved international notation for upper-level derivatives. Because how many primes are you ready to put? If I tell you 17, so you're going to like put 17 primes, and how will I find out it's 17? Will I count? No. So parentheses and the number inside is reserved for the derivative. The pattern is, check it out, change the order. So it will be 1 times c sub 1, 1 times 2 times c sub 2, 1 times 2 times 3 times c sub 3. Agree? See the pattern? It's kind of like a puzzle. 1 times 2 times 3 times 4, c sub 4. And the pattern now is getting clear. What is the tool we have? What kind of function we have that allows us to write down the pattern like this in the faster manner? Factorials. Why you're smiling? Exactly. So dot dot dot. Apparently, I can see the pattern, and this is where this famous international formula. I was told saying famous formula is wrong. Famous can be only people or song, famous song. It should be said known international formula. But in my language, we say famous, so I kind of like saying. Everyone knows this formula. To the nth derivative at A, the coefficients will be n factorial. C sub n. This is very important. From the all mathematics ever existed, this is actually definitely in one of the most important lists. So n also should be a counter. Counter starts from 0, then it's 1, then it's 2, and keeps going forever. Remember, note, what is 0 factorial again? 1, and that's why there's a 1 in front of c sub 0. It's 0 factorial. Do you see? It's very tiny. Note, 0 factorial is 1. That's why this formula makes sense. When you start from 0, you will have c sub 0. So now we know the correlation between coefficients of the power series, functions, derivative, and factorials. Surprisingly, that's not the most important part. The most important part actually to write down formula for this. Because we do usually know the derivative. You don't have to write this down. The formula is very pretty. Let's not mess it up. F at n, fn's derivative usually is known. We can figure it out. N factorial is easy to calculate. You just let your calculator or computer plug it 107, it will figure it for you. What we don't usually know are coefficients. Coefficients have so many applications in the real life. We want to find out that. So we're gonna find this. What are the coefficients? And from here the formula happens. And this is the most important. C sub n, I'll put it in fat. C sub n now has a famous, amazing formula. Can be found as n's derivative at the center, a, divided by the n factorial. That is the rainbow. That deserves a double rainbow, but I don't want. Maybe I can. Let's see. Yes, double rainbow. So that is actually what is the most important. This is the formula for the series coefficients. So formula for power series. Power series coefficients, coefficients. That's my short way to write it down. Coefficients. So it is unique. There's a theorem proves that these coefficients are unique. Let me write it down. So uniqueness theorem, uniqueness theorem, that's very important. In mathematics, when we prove something, we need also to prove that our result is unique. What if we have several solutions for the same answer, plus or minus 1, or plus or minus coefficients? Uniqueness theorem says it is unique. You can check in the book how they prove it, but basically we're working with polynomials, so everything was decent, we did not skip anything, everything was fine. Now, the most important is this, called Taylor series. For now, we're going to do the Taylor first, and then I'll tell you about McLaurin. Taylor, this is my L, series, or Taylor expansion. Taylor series, let's do both. Taylor's series expansion. So you can know both, expansion. So again, in Russian we will say Рядите Лора. In France, Taylor series, whatever it should be sound. In Chinese, in Korean, this is exactly what people teach. Taylor series is so important. We teach it around the world. Taylor series coefficient, Taylor series looks like this. This is the most important part. Any function f of x with some restriction on it can be written as a power series with the coefficients c sub n. So let's write it down. C sub n, x minus a to the n. N is from 0 to infinity. That doesn't really explain anything, so let me rewrite it. The coefficients have a formula. The coefficient has a formula now, and we have the specific practical tool to find them. Find the n's derivative, plug the center in it, and divide by n factorial. That's the formula for the coefficient that are standing in front of the unknown x, or x minus a to the n. And then if you really want to know how, and this is how we're going to be teaching you how to find them one by one, it will be, so I'll be changing colors. Maybe I should have done it right away, more obvious. So C sub n, let me put it in purple now, green, blue, blue. And then this one also. So let me put coefficients in blue. Nice. So now the coefficients will be, the first coefficient is f at a. Nothing to do here. The second coefficient will be the first derivative at a divided by 1 factorial. The first coefficient is 0 derivative. 0 derivative, that's original function, divided by 0 factorial. And 0 factorial is 1. Change the color, multiplied by x minus a to the 1. So have enough space for this formula. It will take lots of space. Plus, the second coefficient will be second derivative at a divided by 2 factorials. X minus a squared. Plus, the third one will be the third derivative at the center a divided by 3 factorial. X minus a cubed, and so on. This is the most important part. Let me put it in a fat, beautiful, red one box. This is important. Very important situation happening here. And that's what we're going to be testing you on, using these formulas. But to test you, I first need to tell you how to use it in practical examples, or else it's a bit challenging. But the more you do it, the more it makes sense, luckily. So formula for now says, let me summarize. We had series before. What is new? Now we know how to find the coefficients for any function with the good properties, though. So it's usually continuous. Basically, it's supposed to have an expansion. For that, it should be differentiable, continuous usually, and so on. So let me do formula number 2. Star, this, let's call it star. Taylor did a good job, got into history by doing this. Taylor did lots of other things, but if you ask around the world, what do you know the name Taylor for? They will say Taylor series expansion. Students do know it around the world, even though there's other things he did. So that's how he got into history for sure. And then McLaurin. There's lots of jokes about McLaurin series. One of the main joke is McLaurin just was, it's a joke, okay? Looked behind the shoulder of Taylor and copied everything. But the only thing he changed, he put the center 0 and now put his name on a series. And it's true, we call it McLaurin series. I mean, it's a joke, okay? He did something more than that. But it's the only difference. The center is 0. So when when a is 0, that is a center, then we call it McLaurin series. And countries around the world did not actually agree how to write his name. As you can see in this table, it's with A, but sometimes A is skipped. Sometimes this U is skipped also. Whatever, just any is fine. I was taught with MC, so McLaurin without A. McLaurin series. Then we're gonna call it McLaurin series expansion. McLaurin, no. Let me know if my handwriting is not good. McLaurin series expansion is the same thing, but with A equals 0. So let me quickly write it down for you so you have some idea. f of x will be sum, but now c sub n, let me not write it down like this, it will be f n's derivative at 0 divided by n factorial, and then it will be just x. That's why it's easier. X to the n from 0 to infinity. And all the coefficients, you plug 0. Let me put it in red. You plug 0 instead of a. So Taylor series is a general case, usually called with a shift. Taylor can be shifted to center 5, 7, minus 3, while McLaurin series only works with 0, center 0, which is, again, it's just Taylor series with a center 0. But okay. What do you think about this for now? And I have notation for you. Internationally, we like to write down Taylor series with capital T. So TH is usually written as a theorem, but capital T with a period, usually Taylor series. And in McLaurin is usually M or MC. MC series. So you'll see I'm using this notation a lot. Okay, very interesting. Let's do something. Example, and let's also start talking about your homework. And this is when you will realize what is going on. I clearly remember I was taking this class. It's exactly with this topic, exactly with this explanation. And I had no idea what just happened, why the professor said it so exciting, who cares? Then we did the example, it was kind of interesting. And then it clicked, like next week, it gets into your brain how interesting this is. So right now it's very technical, just letting you know. But actually it's very important and very extremely impressive, this idea. Example 1. Let's figure out series, find, and let's figure out, if you see in your homework McLaurin series, you know what to do. You plug a equals 0. McLaurin series means a is 0, centered at 0. That's immediately what it means. McLaurin series for the given function. They call it McLaurin series expansion or Taylor series expansion. We're going to figure out the easiest one for now. F of x is cosine x. Interesting. So we had expansions for 1 over 1 minus x. We also found expansion last week for the logarithmic function and even arctangent. But like any function, so anything you've ever met before can have a series, that is pretty awesome. Of course, it should be like nice continuous function with derivatives, but anything. This is how interesting. Anything can have a series. We're learning series is a new tool, and we now can find series for anything. Everything you ever learn, quadratic, cubic, arcsine, but only on a nice domain, and stuff like that. So all the sines and cosines, tangent, arctangent, yeah, let's find these bad boys. That's a weird phrase to say, I don't know. It's from the movie, I heard someone said, anyway. Let's find these guys. Let's see how they were created. This is what I was taught to memorize, but you guys don't have to, that's good. Table, so I'm teaching this solution. I'm teaching this idea with a table. That's just not a requirement. You will see it right now. If you took this class before from anyone else, maybe there was no table. This is just how you organize information. I like organizing everything in a table. I'm an organized person, so I like seeing it in the rows and columns. You don't have to though. I'm putting first the original function, f of x equals cosine x. Now my first column will be derivatives. Now I will, and then leave some space to the right, so it will be a table. Okay, the original function is written. Now I will write down the first derivative. That's exactly what we just did to derive the formula. The second derivative, and so on. As many as possible. Usually we stop like at 5 or 6. So f of x is cosine x. Let's do it quickly. Derivative is what? Minus sine x. Good. Second derivative is? Minus cosine x. Good. Third derivative is? Just sine. Minus minus gives you plus. Sine x. Fourth derivative is? Cosine x. And it basically cycled back. Cosine and sine keep cycling back because they're periodic and they keep giving you each other. That's a pretty cool idea here. That sine and cosine basically give you each other when you differentiate, plus or minus. So we don't need to have more because now we know the pattern already. So the fifth derivative will be minus sine, and so on. Now what we do is we're going to plug the center they gave us to plug. So let's do that. Plug A, whatever it is. Plug center A. It can be some number, but for McLaurin series, it is 0. So I'm going to plug f at 0. That's my original one. F prime at 0. F prime prime at 0. F prime 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 at 0. F fourth derivative at 0. Center can be different. If center is different, we give you the center. We say, find Taylor series around 7. Then you plug 7. What is cosine at 0? It's like either 0 or 1. 1. Remember, sine is the one that behaves normally. Sine at 0 is 0. It starts from 0. Very nice. It's increasing. Cosine is exactly the weird one. Cosine at 0 is not 0. It's decreasing and gives you negative if you differentiate it. F prime at 0 is sine at 0. 0. Actually, you can put zeros everywhere you see sine right away. Second derivative of 0 at 0 gives you what? Negative 1, because there's a negative in front. Fourth derivative of 0 cycles back to the original. So, and the last column is multiply by corresponding factorial pieces. So, let me put it like so. Let me complete here. The last one is, you need to remember the formula. The formula is C sub n is n's derivative at the center divided by the n factorial. Do you see what I wrote, or it's not very good? N's derivative at the center divided by the n's factorial. We found n's derivatives at the center. Actually, I should not put it here. I should put it higher because I have the original function there. Put it higher, like so. And now, yeah, I know, sorry about that. Now you can write down the missing factorials. So 1 will be divided by 0 factorial. 1 will be divided by 0 factorial. That's just 1, because 0 factorial is 1. 0 will be divided by 1 factorial. Well, that's 0. Minus 1 will be divided by 2 factorial. That's not 0. That will be new. 0 will be divided by 3 factorial. And 1 will be divided by 4 factorial. Let me stop because I think nobody just understood what I did. The new parts are these denominators. That's the new parts. The denominators. We found, what is happening here? We found the numerator of the formula. That's what we did. We found the n's derivatives at the center. Now what we do is we're dividing by the corresponding factorial. 0, 1, 2, 3, 4, 5, 7, and so on. Factorials. Because they are in this magical, amazing table. In the denominator, we're dividing by the n factorial. Starting with 0 factorial, but 0 factorial is 1. So I always remember that the first two are always the same. The first two, just copy them because you divide by 1. So it was 1 and 0, now it is 1 and 0. The third one is, I'm taking minus 1, put it here, right? And divide by 2 factorial. 2 factorial is just 2, because it's 1 times 2. Let me write it down for people who don't remember factorials really well. Minus 1/2 is the first answer. So 1 times 2, that's the definition of the factorial, or 2 times 1. The third one is 0 divided by 1 times 2 times 3. At some point, I remember it was 6 all the time. So it's 0 divided by 6, but it's 0 though. In this specific case, it's 0. Then you have 1 divided by 1 times 2 times 3 times 4. What is that? 6 times 4, 24. 6 to 4, 24. Thank you. 1 over 24. And you keep going if you need more. But since this function is repetitive, we're going to stop here. So let me show you why we're doing this. Now we're ready to write down a series expansion for this function we knew since what, like 7th grade, 6th grade, when do you guys learn sines and cosines? I don't know. We do it in kindergarten because we're fancy Ukrainians. Kindergarten. You first learn how to say cup and dog and you're like sine of x. Yes?
I don't have to worry about absolute values.
Absolute values?
Yeah.
Where?
No, I'm asking why don't we do that?
Oh, why we don't?
Yeah.
Very interesting. Plus and minus actually will be pretty important. The sign can be positive and negative, for example, so we need plus and minus to go up and down. So absolute values were for the integral test, for the tests, for the convergence. When we test something, usually minuses and pluses are standing on the way and mess up the test. But this one is creating a formula. Very good question. The question was why we don't put absolute values. Moreover, I want to point out in a second, you will see, we know cosine should be an even function. Let's check if it's true. And we know cosine should be positive and negative at some point. And we know cosine is from -1 to 1. Let's see if all of this is true. Thus, so this is will be the most important table, which we're going to do on the exam 3 and the final exam. For any kind of random function I give you. Thus, cosine x can be written as the next formula. Let me remind the formula star, since double star, that's a McLaurin formula, tells you, let me probably remind like here, so we put it on top of each other. Any function with specific properties should be differentiable on an interval, blah, 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 has this formula. The first, let me zoom out so you can see it. It's a double star, but I did not write it down in terms. Okay, then it's actually very good. The original at 0, let me zoom in, fine, plus it will be the first derivative at 0 divided by 1 factorial x to the 1 plus the second derivative at 0 divided by 2 factorial x minus 0 squared, so that's why it's x squared, plus f3 at 0 divided by 3 factorial. 3 factorial is 6 times x cube x minus 0 cube, so it's just cube, and so on. This is called McLaurin series. McLaurin series expansion. Since we know this formula star star, we can write down the function sine. Sine of x will be, and we just literally want to put one on top of each other. So f at 0, you see my table is exactly what I need here. F at 0 is coming from this second column, right? So, but I actually will be telling you to use the third right away, because it's actually f at 0 divided by 0 factorial. So it's still a pattern. It's the same pattern. 0 factorial, 1 factorial, 2 factorial, 3 factorial. X to the 0, x to the 1, x to the 2, x to the 3. F no prime, f prime, f prime prime, f prime prime prime. So the first one will be 1. It comes from here, the very first row. It's the original oh, that's not sine. We're not talking about sine. Duh. We're talking about cosine. We're finding the function cosine. F of x, which we chose to be cosine. It will be just cosine at 0 divided by 0 factorial. That's 1. Plus, okay, let me show you in different color. It's green. These are the coefficients. These are the coefficients. Whatever is attached to the variable x are coefficients. They are located in this last box, last column. So f prime at 0 divided by 1 factorial is 0 and multiplied by x. That came from the second row. That came from the second row. Maybe it will be helpful to write down. Let's see. Every semester, I don't know how much information is actually needed for students to make it very clear. This is where I got my second coefficient. So this is called, if the first one was C sub 0, the second one is C sub 1. Now we're gonna have finally some numbers. This is my C sub 2. It's a second derivative at 0 divided by 2 factorial. That is C sub 2, the third row of the last column. And it gives you, let's put it just right away, minus 1/2. And then it's times x squared. Minus 1/2 times x squared, or minus 1 over 2 factorial. But 2 factorial is 1 times 2, which is 2. Plus third derivative at 0 divided by 3 factorial. That is C sub 3. That is 0 times x cubed. Plus fourth derivative at 0 divided by 4 factorial. Fourth derivative at 0 divided by 4 factorial. That is C sub 4. 1 over 24 x to the 4 plus, and keep going. So very interesting. If I kick out all the zeros from my view, because I don't like it. Also, how did we get 24? That was 6 factorial. That becomes 1. 0 we skip. Minus 1/2 x squared. 0 we skip. Plus 1 over 24 x to the 4. 0 we skip. Next one will be, well, it's 2, 4 factorial, 6 factorial, 8 factorial. But it's fine. Let's keep going. So cosine x equals this. This is formula for cosine x. And this is called basic McLaurin series for cosine function. If you're asked to collect it, if you're asked to write it down in this sigma notation, then we're going to start from 0 to infinity. We notice several things. It's alternating sign because cosine function can be positive and negative. So it matches with what we learned before. It can go up and down, above x-axis, below x-axis. So it's positive and negative, positive and negative. Alternating sign can be written as minus 1 to the n. It's alternating series. So let me write the sequence of notes. Note 1, it's alternating series, that makes sense because cosine can be positive and negative. 2, cosine is an even function. Not evil, even function. That means there should be no cubes and fifths and so on. It is true. Everything that had even power was 0. That makes sense. So now it matches everything we know about that as well. So we're going to write down, how to write down even function anyways? X to what? How to write down even numbers? 2n, right? 2n, and then you just need to know where to start, from 1, from 0. So if n is 7, which is odd, 7 times 2, 14, even. Makes sense. And then we notice this idea. When you have 2, it's divided by 2 factorial. When you have 4, it's divided by 4 factorial, which that's how we got 24. So that means the pattern will be, if you have 2 to the n as power, we're going to divide it by the 2 to 2n factorial. And that is the famous known formula for the cosine function McLaurin expansion. So, alternating even function. Do we know the graph for this function? Yes. The graph for this function is at 0, what should it be? When I plug n equals 0, it will be minus 1 to the 0, x to the 0 is 1, n factorial when it's 0 is also 1, starts from 1. It is positive, and then the sign changes to negative. That's why it's alternating. And it's even. Even function, alternating plus and minus. And that's exactly what this series tells us. So that is true. Now, when you go back to the table I gave you at the very beginning, it's nice if you have this table in front of you for a couple of weeks, until the end of the class, actually, it will be important. Cosine function, here it is, 1 minus, if it was squared, divided by 2 factorial, 4 divided by 4 factorial, 6 divided by 6 factorial, to the n divided by 2n factorial. While sine, so let me put some notes. Cosine is even, no, let me actually put it here. We know that cosine is even, so that's why I could memorize by myself that it should have 2 to the n power, or 2 times n factorial. We also know it's alternating because cosine and sine can be negative and positive. Sine function is also alternating. It can be positive and negative, but it's odd. That's why I remembered that it's 2n plus 1, 2n plus 1, see? And it has cube, 5, 7, odd powers versus 2, 4, 6, even powers. Check it out, one more thing. Sine at 0 is 0, right? We know that. And it's true. If you plug 0, everything becomes 0 for sine. While cosine at 0 is 1, and it's true, it's exactly what is happening over here. When you plug 0 into cosine, it gives you 1. So it matches. The formula works. Well, thanks God. It's used everywhere in engineering. We would not have planes flying if this formula doesn't work. So everything matches with what we know. Exponential function grows very fast. We know it, so it's all positive. Exponential function cannot be negative. Remember, e to the 7 is positive. E to the 0 is 1. So e to the 0 is 1 matches with this part. And it's growing really fast, as you can see. It's exponential. Yes, I think it's someone's phone. TED Talk. No problem. It's like, yeah, definitely it's not the conversation outside. So, e to the x grows very fast, blah, blah, blah. Logarithm and 1 over 1 minus x came from the geometric series. But all kind of function now will be working very hard to find different functions. Some just made up from scratch, someone that we know really well. Last 4 minutes, I will show you this amazing thing, which will be... No, don't do that. Okay, good. So it's going to be, say, we did cosine, McLaurin series. Cosine. Okay, it did change to A, but doesn't really matter. This is how it looks. Check it out how awesome this is. What we did, this is from Wikipedia, for example. What we did was, we're creating those polynomials. Let me show you again. This is actually pretty awesome. When we finished creating it, what I noticed was that the first polynomial is just constant 1. The second polynomial is parabola, it's x squared. Then it's going to be x to the 4. Then it's going to be x to the 6, which matches with this formula we did here. So, like this is just a parabola. Then it's fourth power. The more you add, the more power it gives us. This animation shows exactly that. We first start with the coefficient. The more power you add to this series expansion, the more wiggling it becomes. Because polynomials go up and down as often as the power. If the power is x to the 6, it will go up, down, 6 times. If it's 17, it goes up, down, 17 times. The more powers you add, the more wiggly the polynomial becomes. So this is exactly how we were figuring out the sine, cosine, and other functions, in this case cosine. We will keep adding more and more powers to it. But since it's even, odd powers disappeared because they had coefficient 0 in front of it. And in all even state, and the more you add to them, the more they're covering the sine cosine function. See, the more polynomials we add, the more interesting it becomes. And in general, yeah, this is basically what we give you in a test. We want you to figure out those coefficients, how to put them in Now we know the formula. You find corresponding derivatives. You plug corresponding center. In this case, it was 0. Let me see if this one is also working. That's sine. Oh, fine. Not work. Oh, here it is. Taylor polynomial. That's a sine function. The more you add, the more wiggly it becomes. Why it's so important? Because when it's wiggly, it gives better approximation for functions we don't know. Sine and cosine we know really well. But what if I ask you to find sine of square root of n divided by arc cosine multiplied by logarithm e to the 17x? We're going to do Taylor series for that. We're going to approximate everything you hate so much with polynomials. Why? Because we like polynomials. Because derivative of x to the 7 is 7x to the 6. Simple as that. What is derivative of sine of square root of x divided by arc 7 e to the 70x times logarithm? So we're going to approximate all the horrible stuff with polynomials because it's so convenient. And that's where it blew up. The space science, the microbiology is using Taylor series for everything. And then we're going to do it on Wednesday. Good job, people, for paying attention.